All right, let's get straight into it. We're diving deep into AQA's required practical on thermal insulators. This is everything you need to know to absolutely smash any exam question that comes your way on this topic. So let's be honest, you probably did this practical ages ago, right? You remember some beakers, maybe a thermometer, but what do the examiners actually want you to have locked in your brain? Well, that's exactly what we're going to break down right now. Here's the game plan. We'll kick off with the core task itself, then we'll walk through how to design the investigation and make sense of the results. After that, the really important bit, we'll tackle some classic exam questions and then finish up with the absolute must-know takeaways. Right, first things first. Before we get into all the fiddly details of how to do it, we need to be totally crystal clear on the what and the why of this whole investigation. Okay, pay close attention here because this sentence is literally pulled straight from the AQA specification. This is the official mission objective. Your job is simple. Find out which materials are best at stopping heat from getting out. That's it. It's that fundamental. So, what even is a thermal insulator? Well, in simple terms, it's something that's really good at trapping heat. But for the exam, you need the sciencey bit. It's a material that reduces the rate of energy transfer. And here's the killer phrase you need to remember. Thermal conductivity. A great insulator always has low thermal conductivity. Okay, let's switch gears and talk about the design phase. You know, exam questions love to test your ability to think like a proper scientist. They don't just care about what you did, they want to know why you did it that way. So this is the basic blueprint for any solid scientific experiment. You start with a guess, a hypothesis, then you figure out your variables. Grab your kit and write down your plan. We're going to zoom right in on those variables because that's where the easy marks are hiding. This table is your new best friend. Seriously, you have got to know these three inside and out. Your independent variable is the one thing you deliberately change. In our case, the material we're testing. The dependent variable is the thing you measure to see the effect. That's the temperature drop. And then you've got the controls. Everything you have to keep exactly the same to make it a fair test. We're talking the same amount of water, same starting temperature, same thickness of insulation, and measuring over the exact same amount of time. Nailing these controls is absolutely critical. Right, so you've done the experiment, you've got a table full of numbers. What now? Well, this next part is all about taking that raw data and turning it into a conclusion that actually means something. A simple bar chart like this is a brilliant way to show your results. Now, look closely. Here comes a classic exam trap. You might think the biggest bar, the biggest temperature drop means it's the best. Nope. The whole point is to stop heat loss. So, the material with the smallest temperature drop is the best insulator. Looking at this chart, polystyrene is our champion, no question. And here it is, a perfect gold standard conclusion. Just look at how it packs three crucial things into one sentence. First, it makes a clear claim. Polystyrene was the most effective. Then, it gives a scientific reason, because it allowed the lowest rate of energy transfer. And finally, it links it all back to the evidence from your experiment, resulting in the smallest temperature drop. Claim, reason, evidence. You write that? You're getting top marks. Okay, let's quickly nail two words that pop up all the time in evaluation questions: accuracy and precision. Accuracy is all about how close you are to the real answer. Precision, on the other hand, is about consistency. It's how close your repeated measurements are to each other, even if all of them are wrong. Now, this slide breaks down the two main types of experimental error. And honestly, examiners love this stuff because spotting errors and fixing them shows you're actually thinking like a scientist. Random errors are those little unpredictable hiccups, like misreading the thermometer. The way you fight these is by taking lots of repeat readings and calculating an average, a mean. Systematic errors are different. They're consistent problems, like a dodgy thermometer that always reads 2 degrees too high. You can only fix those by fixing your gear or your method. Okay, we've covered the theory. Now for the main event, taking all that knowledge and applying it to the exact styles of questions you're going to see in that exam hall. Ah, a classic control variable question. So why use the same amount of water? Well, think about it. A bigger puddle of water has more thermal energy, so it's going to take way longer to cool down, no matter what you wrap it in. By using the same volume every time, you make sure the only thing you're really testing is the insulation material itself. It's all about making it a fair test. Okay, here's a slightly tougher one on errors. A perfect example of a systematic error would be a thermometer that's not calibrated right. Maybe it always reads 1 degree too low. How do you reduce it? Well, you could check it against known temperatures, like putting it in boiling water to see if it reads 100 degrees, or you could just use a different, more reliable thermometer. Now, this is a question that tests your wider physics knowledge. So, why stick a lid on it? Because a massive amount of heat escapes from the top surface of the water through convection and evaporation. By putting a lid on, you block that main escape route, which means you're much more focused on measuring the heat that's being transferred through the sides, through the insulator you're actually trying to test. All right, let's pull all of this together. Think of this as the rapid-fire summary. If you're going into the exam, these are the critical points you absolutely have to have down. First, variables. Know your independent, dependent, and controls like the back of your hand. Second, your conclusion. The best insulator is the one with the smallest temperature drop. Don't forget that. Third, errors. Know the difference between random and systematic. Fourth, evaluation. Be ready to suggest simple improvements, like using a lid or doing repeats to find a mean. And finally, the theory. Always link everything back to that key idea of thermal conductivity. Good insulators have low thermal conductivity. And at the end of the day, this isn't just about passing an exam. The principles you've been testing are used literally everywhere, from the big stuff like the insulation that keeps your house warm to the flask that keeps your drink hot. So next time you grab a takeaway coffee, just think about it. How are the ideas from this very practical being used to engineer that simple cup? That's physics in action right there.